Hello guys, my name is Balkrishna Srivastava and welcome to Code with BK. So in this video, we write a C++ program to check if an integer n is a prime number or not. So before we begin, it is a request to please subscribe to my channel because out of 100 viewers, only 3 to 5 are subscribed. More than 95% of my audience is not subscribed and a subscription is very important. So please do subscribe to my channel. So let's begin. So we have to write a C++ program to check if an integer n is a prime number or not. And we see two approaches to solve this problem. The first is using the brute force approach and the second is using the optimized approach. So in the brute force approach, we just want to solve the problem. We don't make any kind of optimizations, okay? And in the next method, we try to make it as fast as possible, okay? All right, so what is a prime number? A prime number is an integer which is divisible by 1 in itself, okay? Examples of prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23 and so on, okay? 1 is neither prime nor composite, okay, right? So let's look at the brute force method first. So suppose if we take an example of n equal to 10, okay, and we need to check if this is a prime number or not. So basically we need to find a value I between 2 to less than n that can divide n completely, okay? So if we are able to find a value I that completely divides n between 2 and less than n, greater than or equal to 2 and less than n, it means n is not a prime number. So if you find a factor I, n is not a prime number. If you are not able to find a factor I, it means n is a prime number because n is divisible by 1 n itself only, okay? And 1 is neither prime nor composite, okay? It comes in neither, okay? 1 is neither prime nor composite, okay? All right, so how do we find if there is a factor of n between 2 to n? So we can generate values of I, okay, from 2 to less than n. So for case of n equal to 10, we get values of I 2, 3, 4, 5, 6, 7, 8 and 9, okay? If any of these values can completely divide n, it means we have found a factor I, right? So in this case, we have 2 and 5, okay? 2 divides 10 completely, 5 divides 10 completely. But how do we check if a value I divides n completely? In the code, we say n% I equal to 0. Okay. Now, percent is a modulus operator. Okay. In short, we call it a mod operator. Okay. So, a%b, where a and b are integers, returns remainder when a divided by b. Okay. So, a%b will return 0 if a is completely divisible by b. For example, if you do 5% 3, okay, this is going to return you 2 because 3 ones are 3 and remainder is 2. Similarly, if you do 10% 3, okay, 3 3 is a 9 and remainder is 1. So a% b equal to 0 will make sure that b completely divides a, that is b is a factor of a, that is if we have 10% 2, okay, 2 5 is 10, remainder is 0. Similarly, 10% 5 will return 0 because 5 to z and remainder is 0. Okay, so we can check if I is a factor of n using mod operator and we can generate these values from 2 to less than n using a for loop. Okay, so in short, summarizing this, all we have to do is generate values between 2 to less than n. Okay, and if any of these value I completely divide n, it means we have found a factor of n apart from 1 n itself. It means it is not a prime number. If we do not find any factor I, it means it is a prime number. Okay, and that's what we do in our code. Okay, so I am going to write for int I equal to 2, I less than n, I plus plus. Okay, generate values from 2 to less than n. If any of these values completely divides n, it means we have found a factor of n. If it means it is not a prime number, I return false. Finally, I return true. Okay, that is, after the for loop completes, we are writing return true because for loop will be over and we will be able to reach here only if this never happens. Now, if this never happens, because this never happens. Now, this never happens means we never found a value I that would completely divide n. That is, we did not find a factor of n between 2 and I. Okay, so finally we return true to tell this is a prime number. Okay, so this method takes an integer n, returns a boolean value, returns true if this n is a prime number, otherwise returns false. Okay, so in my main, take an example n equal to 10. I'll say cout is n a prime number. Okay, we can use the return value of this method. Okay, plug it into a ternary operator. So I say if the return value is true, I print yes, else I print no. Okay, and then change it. Okay, so let me compile and run. For I need to return false here, okay, because this cannot be empty here. Okay, so clear and compile again and run. Okay, 10 is a prime number. No, let's take another example, say 5, compile, run. Okay, let's take another example, say we can pick any, say 23. Okay, compile and run. All right, we can also find prime numbers within a range. Okay, for int I equal to, say, start from 2, I less than equal to, say, 100, I plus plus. Let's start with 1. Okay, or I'll take int n equal to 100 separately and I'll keep it less than equal to n. Okay, let's keep it 25 first. Okay, so see out prime numbers less than n are. Okay, so we are looping for values between 1 to less than equal to n, which is less than equal to 25, and we print I if it is a prime number. So if is prime, I'll say I'm going to print I. Okay, clear, compile, run. So prime numbers less than 25 are 1, 2, 3, and I'll need to change this line so that we get prime numbers from the next line. Clear, compile, and run. Alright, prime numbers less than 25 are 1, 2, 3, 5, 7, 11, 13, 17, 19, 23. Okay, but we have one in this case as well, which is wrong. Okay, and that is because when you pass 1 to this function, okay, loop starts with 2, I equal to 2, I is less than n. So for n equal to 1, 2 less than 1 is gonna be false. So for n equal to 1, this loop never runs and you return true. Okay, so for this case, you handle the case for 1 separately. You say if n is 1, I return false. Okay, now when you clear, compile and run, okay, you don't get 1 as a prime number. Okay, let's make till, say, 100, compile, run. Okay, 97, 80, 93, 29, 31. Okay, so this was the brute force method to check if an integer n is a prime number or not. Okay, so moving to the second method that has an optimized approach. Okay, so the idea remains the same, that we have to find a factor I between 2 to less than n that can completely divide n. So how do we optimize this? Okay, so the first thing we do is add the case for 1. If n equal to 1, we return false. Okay, then we add another case that if n equal to 2, we return true. And I'll tell you why we are doing this, because in our third case, if n% 2 equal to 0, we return false. Okay, that is to say that 2 is my only even prime number. Okay, only 2 is the only even prime number. Apart from that, there is no other number that is even and prime, because for all the other numbers greater than 2 which are even, 2 is going to be their factor. Okay, and since they have a factor apart from 1 and themselves, that is, they are not prime numbers. Okay, so we are able to eliminate all the even numbers out apart from 2 itself. Okay, that's why we take the case of 2 first. If n is 2, we return true. If n is not 2 and n is an even number, okay, all even numbers greater than 2 are not prime numbers, we simply return false. Okay, we don't need to do any other checks. We know it is divisible by 2. Okay, if I consider values, say we took n equal to 25, so this is the range. Okay, you can say, okay, you can make this L, you can make this L. Okay, okay, so if I have sorry, not this, L equal to 25. Okay, find all prime numbers less than L. So let me write all numbers less than L. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and 24. Okay, we have eliminated all the even numbers. Okay, because they are all divisible by 2. Okay, now for all the other numbers, okay, we just need to optimize this process. Okay, generating the values of I and then checking if any value I completely divides n. Okay, so rather than starting from 2, we start from 3. Okay, and we skip every other value. Okay, that is in your previous case. Okay, Your for loop was starting was 2 and it was I plus plus, so it was from 2 3 4 5 till the value less than n. Okay, in this case we write a for loop that starts from 3 and skips every even value. Okay, so instead of generating values of I which are 2 to less than n, we generate values of I. Okay, for n equal to 10 we start from 3, okay, and skip every other even value, so 3 5 7 and 9. Okay, 3 5 7 and 9. Okay, and then we check if any of these values divide n completely. All right, so in that case we get 5, so n is not a prime number. Okay, that's the first optimization that we make. Okay, the second optimization is we do not go till n. Okay, we go I less than equal to sqrt of n, and this is a major optimization. Okay, but because it significantly reduces the runtime of this for loop. Okay, and why we go till less than sqrt of n? Okay, I'll tell you. So suppose you have value m equal to a into b. Okay, now there are two things: m is a prime number or m is not a prime number. Okay, m is greater than 1. Okay, so suppose it is not a prime number. Okay, now since m is not a prime number, it will have a factor apart from 1 and m itself. It means that is a value of I greater than equal to 2 less than m that can say m% I equal to 0. Okay, so I is a factor of m. Okay, so let's just consider the value m by I is say k. Right, that is when you divide m by I, the quotient is k, the remainder is obviously 0 because I is a factor, right? It means m is equals to k into I. Okay, and I is the factor of m. That's what we discussed, greater than equal to 2 less than m. Okay, now since I is a factor of m and m equal to k into I can say both k and I, both k and I cannot be greater than square root of m. Okay, and why this is so? Because suppose if they are both greater than square root of m, then this k and this I is a value greater than square root of m. That is, you do square root of m, some value greater than root of m into some value greater than square root of m will give you a value greater than m. So this equality will not hold. Okay, that is to say one of k and I will be less than equal to square root of m. Okay, that is to say you will find one of these factors, because I is a factor, so k is a factor too, because if m% I equal to 0 and m by I give k will also be equal to 0, because m by k will give you I. Okay, so the point of telling you all this is that you will definitely find a factor, okay, of m which is I less than equal to square root of m if m is a prime number. If m is not a prime number, you won't find it. Okay, that is to say if you just need to find a factor of m less than m, you just need to go till the square root of m. Okay, so instead of going to less than n, here we go till I starts from values 3 to less than equal to square root of n. Okay, and this is the entire explanation. Okay, there is a link for this explanation. I'll add a link in the description of this video. It's a Stack Overflow description, you can take a look at it. So I include C math, okay, and I say I is less than equal to sqrt of n, and then the same thing, if n% I equal to 0, return false, finally return true. Okay, so we are again just finding a possible factor of n that can completely divide n. We are just reducing the number of values of I that we need to find. Okay, and there's some math involved behind that. Here we are just simply finding all the values of I between 2 to less than n. Okay, now if we take another example, okay, say n equal to say a prime number, I'll say n equal to 19. Okay, square root of 19 is going to be 4 4 is 16, 5 5 is 25, 4 point something. Okay, so I will take values starting from 3 in increments of 2 to less than equal to 4 point x, that is less than equal to 4. Okay, so 3, then it's supposed to take 5, but 5 is not less than equal to 4, so I only takes 3 compared to the values I would have taken 2 3 4 5 6 7 8 9 10 11 12, 13, 14, 15, 16, 17, and 18. From 2 to less than n, okay, in our brute force case, okay, and only 3 in our optimized case, okay. And we know n is a prime number because the value, if there is a possible factor of n, we'll find it less than equal to the square root. There is not. 19 is not completely divisible by 3, so this is a prime number, okay. Let's take a non-prime number value, say 25. Square root of 25 is 5. So I takes values 3, then increments of 5. So less than equal to 5 will be, this will be allowed, okay. So I takes values 3 and 5 for 25, and we find a value 5 that completely divides 25. So 25 is not a prime number, okay. Instead of taking values 2, 3, 4, 5, 6 till 24, okay. So number of values of I generated are much less in the optimized case, okay, right. So let me just change is prime 1 by is prime 2, and we'll see the same output, okay. So clear, compile, run, okay. You see the same set of values, okay. And to check our optimized method, we can say if is prime 2 is not equal to is prime 1, okay, okay, we can say error at I, okay. Otherwise we say all good, okay. So we should not be getting a single line of output from here, because these two methods should calculate the same true or false or the same value of I prime or not, okay. So clear, compile, run, okay, all good. We are printing this message, we can take this message out as well, okay. So compile and run, okay. I change this to say 1000 or say 10,000, compile, run, all good. We can change this to 10 to power 5, compile, run, okay, all good. Took a little more time because we are iterating to 10 to power 5 values, and this loop will take time for 10 to power 5 values, okay. All right. So this was your C++ program to check if an integer n is a prime number or not, and we saw a brute force method. We just wanted to get the right solution, no optimizations, and then we saw this optimized approach, which is a very standard code. Okay, you can absolutely remember this as it is, and you can use it in C++, C as well, Java, C Sharp, Python, or JavaScript, or any other programming languages, right? Because the idea remains the same. Okay, you eliminate out cases to generate minimum number of values of I for which you need to check if I is a factor or not. Okay, so this was a C++ program to check if an integer n is a prime number or not, and I hope this was helpful. So if there are doubts, if there is a part you do not understand, please let me know in the comments. I always try to answer all your comments, and you can also let me know in the comments if there's a question you want to solve or if there's a concept you want to discuss. So please let me know your thoughts about this video in the comments. Please like this video, subscribe to my channel, and thank you for watching.